Hey girls, welcome back. We have one more chapter to finish up Unit 2, which was all about quadratic, polynomial, and rational functions. And in this chapter, we are going to be focusing on these inverses and radical functions. And first, we're just going to talk about finding the composition of functions. So this is in your book, Chapter 5, Section 2. You've already learned when we did the polynomials chapter a lot about functions, like adding functions together, subtracting them, multiplying them, and dividing them. But now we're going to do something called composing them. So a composition of functions just means that you're taking one function and you're plugging it into another one. If it is written f and then a little circle g of x, you have to pay attention. That little circle, it's different than if it has a dot. A dot means multiply, but a circle means of. So this is saying f of g of x. You could also write it like this, f of g of x. I like it written like this better, but really either way, you'll be able to tell that the second one that's listed, it's saying plug that second one, so the g function, into the first one, the f function. Let's take a look at an example to see what that really means. Example 1 says, given that f of x equals x squared minus 4 and g of x equals 2x plus 1, evaluate each of the following. So f of g of x, it's saying take the g function and plug it into the f function. So I already kind of drew us an example here. We're taking the g function, 2x plus 1, and we're plugging it into the f function. So it might be helpful for us to write f of 2x plus 1. Now it looks exactly like something that we've done before in our polynomial chapter. We know how to do f of 2x plus 1. It means we're going to replace the variable with 2x plus 1. Since f of x is x squared minus 4, instead of putting x squared minus 4, we're going to make this say 2x plus 1 squared minus 4. So essentially what you're doing is you're just replacing the variable in the f function with the entire g function. Once you have it set up, now you just have to simplify it. So think of PEMDAS. This, you can't really do anything in this parentheses, but you can evaluate the exponent. So in order to square it, we know that means we're going to have to take 2x plus 1 and multiply it by itself, 2x plus 1, bring down your minus 4. Let's FOIL this out. 2x times 2x would be 4x squared, 2x times 2x would be 2x, 1 times 2x would be 2x, and 1 times 1 would be 1. Bring down your minus 4. Now combine like terms, you get 4x squared plus 4x minus 3. So that's the answer for f of g of x. But it also said to state the domain and range. For this function, it's a quadratic function since it's x squared. So I know the domain is going to be all real numbers, as it is for most of my functions. And my range is going to depend on the vertex. So let's do some review. In order to find the vertex of a quadratic, I follow the formula negative b over 2 times a is the x value. So I'll go negative 4 over 2 times a is also 4. So that makes 4 over 8 or a half for my x value. But the range really depends on the y value. So now in order to get the y value, I have to go back and plug that back in. So I'm going to do 4 times a half squared plus 4 times a half minus 3. Exponents come first. A half times a half makes a fourth. Next, I can multiply 4 times a fourth. You can put that 4 over 1 if it helps you to see. The 4's will reduce down to 1 and 1. So you really just get 1. Again, for this 4, you can put it over 1. The 4 and 2 can reduce down to 1 and 2. So we get plus 2 minus 3. 1 plus 2 is 3. 3 minus 3 is 0. So the y value is 0. So my range, let's see, does this open upward or downward? It has an a value that's positive, so I know it's going to open up. this vertex is 1/2, 0, but the range only depends on the y value. The lowest y value of the parabola is 0, the highest y value is infinity. Now this is similar, it's saying g of f of 3. This time it's just a little different because there's a number here instead of an x. So you have a couple options. You could do like the composition of functions first and then plug in the 3. Or what I would suggest doing here is just do one step at a time. So you're going to work from the inside out. So first just figure out what's f of 3. F of 3 just means you're plugging in 3 to the f function. So you're going to take 3 squared minus 4. 3 squared minus 4 we know would be 9 minus 4 or 5. But this wasn't just asking us for f of 3. It's asking us for g of f of 3. So let's fill in our g on every line here so that we can see now what we're trying to do is g of 5. So now to do g of 5, we look at our g function, which is 2x plus 1, and we go 2 times 5 plus 1, because we're looking at the g function, and we're replacing the variable with a 5. So 2 times 5 is 10, plus 1 makes 11. So you just work from the inside out. So do f of 3 first, get the answer, whatever you get, plug it into the g function. Then do g of 5. Whatever you get there, that's your final answer. Go ahead and try these two practice problems now. And here are the correct answers for that. We got 730 for A and 3x cubed minus 3 for B. All right, now let's go down to goal 2. We're talking about finding the inverse of a function. So you have to know that about inverses, two relations are inverses if and only if one relation is going to have the point A, comma B, the other relation is going to have the point B, comma A. So essentially what's happening here is you're switching the input with the output. You guys have actually talked about inverses before in geometry class when you learned about inverse trig functions like inverse sine, inverse cosine, inverse tangent. And you learned about how using inverse sine, inverse cosine, and inverse tangent, it would switch your function around so that you could find the angle of the triangle that you were missing. So instead of plugging in an angle and getting a side, you were using the inverse so that you could plug in the side and get the angle. So notice how that's switching. That's exactly what an inverse function is. Every time it's a function, since you're switching these inputs and outputs, essentially you're just switching the x values and the y values for an inverse. So this is going to look like on the graph, it's going to be a reflection over the line y equals x, which I drew for us here. We know how to do reflections over that line y equals x. We learned that in geometry class. You just switch the x value with the y value. The inverse will only be a function if the original function was 1-to-1. Because remember, 1-to-1 means it has to pass the horizontal line test. So if you're switching the x and y, then the inverse function will pass the vertical line test, meaning it's a function. So since the x and y switch for inverses, you also have to remember that the domain and range will switch. Two inverses will always undo each other. Think about like inverse operations like adding and subtracting, those undo each other. So when you compose inverse functions like what we were doing in goal 1, when you do a composition, everything will get canceled out and you would just be left with an x. An example of inverse functions includes x squared and square root x. Those are inverse functions because they undo each other. Here's the steps to find inverse functions. There's 4 steps, and we're going to do some examples of that now. All right, let's try those 4 steps with an example. Here's the first one. It says, find the inverse of the function. State the domain and range for both f of x and f And that little -1 means inverse, so you're just going to read it as f inverse of x. And it says check your answer. So step 1, it is to replace f of x with y if necessary. It is necessary here because this one says f of x, so we're going to just replace that with y first, step 1. Also in step 1, it says check the horizontal line test. So it's going to be helpful to remember your parent functions. This one is linear, so we know its graph looks like a straight line, which does pass the horizontal line test. So what that tells us is since the original function passes the horizontal line test, it's telling us that the inverse will also become a function. Step 2 says switch the x and y in the function. So step 2, we're going to go, instead of y equals, it's going to say x equals 2y minus 5. Step 3 is to solve this new equation for y. In other words, get the y by itself. So first, add the 5 over to the other side. And next, divide everything in here by 2. So let's write it as a nice function in the correct form. It's in slope-intercept form. It's still a straight line because it's still x to the first power. And finally, step 4 says to replace y with f inverse of x. So we're going to say f inverse of x equals 1/2 x plus 5/2. That's your answer for the inverse. So you'll notice, in the original function, you were taking x, you were multiplying it by 2, and you were subtracting 5. If you had written this, instead of dividing every single term by 2, you could have also written this as x plus 5 over 2. So notice, instead of multiplying by 2 and subtracting 5, you're adding 5 and dividing by 2. Every single operation in the function is inversed. So instead of subtracting, it's adding. Instead of multiplying, it's dividing. And you also have to go in reverse order. So instead of multiplying first, then subtracting, you're adding first, then dividing. That's what an inverse does. Every single thing in the function is inverse. In the instructions, it said to state the domain and range for both f of x and f inverse of x. So for my original function f of x, my domain is all real numbers. And my range is also all real numbers because it's a straight line. In my inverse function, my domain and range will be switched. So I know the domain is going to be all real numbers. My range is going to be all real numbers because if I switch them, they're still the same thing. But for this function, it makes sense. My inverse ended up as also a linear function, so that's going to have a domain and range of all real numbers. In the instructions, it said to check this answer with compositions. So let's go ahead and do that now. In order to check your answer with compositions, here's what it's going to look like. You're going to do f of g of x first. So this should give us a good review of our goal 1. Sorry, instead of f of g of x, we're going to do f of f inverse of x. So we're taking our f inverse, which is, we're going to use this format x plus 5 over 2, and we're plugging it into the original function. I just think this way is maybe easier to work with than the slope-intercept form where we have fractions. So in order to plug in x plus 5 over 2 into the f function, I know I'm going to replace the variable with x plus 5 over 2. So it's going to be 2 times x plus 5 over 2 minus 5. I'm just replacing the x with x plus 5 over 2. So simplify that. The 2's will cancel out. So we have x plus 5 minus 5. Since I went ahead and did the multiplication by 2 and it canceled out, I can drop those parentheses. So I end up with x plus 5 minus 5, which just simplifies down to x. So far, that's good. When you plug in 1, you simplified it down to all the way to x. Now you have to check it the other way around. F inverse of f of x. So this time, we're going to take whatever f of x is, which we know it is 2x minus 5, and we'll plug that into the inverse function. So we have to do f inverse of 2x minus 5. So it's kind of up to you what function form do you want to use. Do you want to use the x plus 5 over 2, or do you want to use the fraction form? Let's just go ahead and use the fraction form here, my slope-intercept form. It's 1/2 times x, so 1/2 times 2x minus 5 plus 5 over 2. So I'm just replacing the x value here with 2x minus 5. So I'll distribute my 1/2. 1/2 times 2 is just going to make an x. 1/2 times negative 5 is negative 5 over 2. Bring down my positive 5 over 2. Negative 5 over 2 plus 5 over 2 cancels out, and you end up with just x. So when you check it and you plug in the composition both ways, you have to check it both ways, and you should get x both times. So this one we know it's correct because the composition both ways simplifies down to x. Now let's do one more example. F of x equals x squared plus 1, and it says we can check this answer with graphing. So step 1, replace f of x with y. So y equals x squared plus 1, and do my horizontal line test. I know that x squared plus 1 is a parabola shifted up 1 on the y-axis. So here's what my parabola looks like. Since it's a parabola, that's not going to pass the horizontal line test. We learned that a parabola never passes the horizontal line test. So what this is saying, since it does not pass the horizontal line test, it's saying that the inverse will not be a function. Well, maybe I shouldn't write it as a function then. So let's say the inverse not be a function. It will not pass the it will not pass the vertical line test. Since this doesn't pass the horizontal line test, the inverse will not pass the vertical line test. Alright, but we can still find the inverse. It's just not going to be a function. It's going to be an inverse relation. So step 2, we'll switch our x and y. So it's going to say x equals y squared plus 1. And then step 3, we solve it for y. So to get y by itself, we're going to subtract 1 on both sides. And then to get y by itself, in order to get rid of a squared, we learned that in the quadratic chapter. When we did complete the square, we learned that to get rid of a squared, you do the square root. But when you square root both sides, remember you have to put plus or minus. So that's what's making this not a function, is because you really have two different things here. Step 4, we can't write this as an inverse function, but what we can do is we can say y equals positive square root x minus 1 and y equals negative square root x minus 1. Since you can't write this all as one equation, that's how you know this is just not going to be a function. So let's think about what this graph looks like. The first one, maybe we'll color coordinate these. Actually, I don't know, this is fine. Separate. This will be less confusing. Separate graph. So I have my x-axis, my y-axis. The first one is y equals square root x minus 1. Remember, your square root function, the parent function, it's kind of like an eyebrow shape. It's the top half of a parabola. but this function has been shifted to the right by 1. So now it looks like this. My other function, negative square root x minus 1, it's also my square root function shifted to the right one, but it's also reflected over the x-axis. So it looks like this. So notice together, those two graphs make a sideways parabola. If you were to reflect that exact parabola over the line y equals x, you would end up with the parabola that we started with. So the parabola shifted up 1 on the y-axis. So that's why the graphs of x squared and square root x look so much alike, but it's only the top half because it has to pass the vertical line test. So the square root of x, it just cuts off the bottom half when it's reflected over in order to make it a function. So that's why in the beginning when we were talking about parent functions, we said we'll talk more about why the square root x and x squared look really similar later on in chapter 5. This is why. It's because they're inverses, but it can't do the whole sideways parabola because then it wouldn't be a function. So that's why it's just the top half. All right, I have 2 examples for you here. I need you to find the inverse of each function, state the domain and range for each. Before we start that, let's actually try the domain and range for this one. For the original function, the domain would be all real numbers. Range would go from 1 to infinity. But then for my inverse, it's not really a function. So let's just take a look at the domain would only go, it's the x values, so since this is an x value of 1, it would go 1 to infinity. But then the range for this entire graph, I know it's not a function, but consider them both, the blue and the purple. If we look at both of these together, the range would be all real numbers because it would go down forever and up forever. So notice that the domain and range are switched. That's helpful to remember. All right, go ahead and pause the video now and try the practice problems, and then come back when you're ready to look at the answers. Here's the correct answer for A. They're linear, so they both have the same domain and range, all real numbers. And then here is the correct answer for B. This one, like you can see, the inverse is not a function. So the inverse has the domain and range switched. You could have also written that as 0, infinity, which I'm sure you guys did. I had it in inequality notation, but you can also put interval notation. That's completely fine. All right, guys. That's the end of this lesson. We learned about compositions and we learned about inverse functions. Tomorrow we are going to come back and talk more about that square root parent function. So I look forward to seeing you then. Bye, everyone.